कुछ आया आपकी स्क्रीन पे?
So the first robots talk about is called Strider. It stands for Self-Excited Tripedal Dynamic Experimental Robot. It's a robot that has 3 legs, which is inspired by nature. But have you seen anything in nature, an animal that has 3 legs? Probably not. So why do
Is
I
the voice audible?
Yes, sir.
Yes, sir.
चलो
Yes, sir.
साफ दिख रहा है ना? ठीक.
call this a biologically inspired robot? How would it work? But before that, let's look at pop culture. So, you know, H.G. Wells' World of Worlds novel, a movie, and what you see over here is a very popular video game. And these fiction, they describe these alien creatures and robots that have 3 legs that terrorize Earth. But my robot Strider does not move like this. So this is an actual dynamic simulation animation. It's going to show you how the robot works. It flips its body 180 degrees. It swings its legs between the 2 legs and catches the fall. So that's how it walks. But when you look at us human beings, bipedal walking, what you're doing is you're not really using a muscle to lift your leg and walk like a robot, right? What you're doing is you really swing your leg and catch the fall. Stand up again, swing your leg and catch the fall. You're using your built-in dynamics, the physics of your body, just like a pendulum. We call that the concept of passive dynamic locomotion. What you're doing is, when you stand up, potential energy to kinetic energy, potential energy to kinetic energy. It's a constantly falling process. So even though there's nothing in nature that looks like this, really we're inspired by biology and applying the principles of walking to this robot. Thus, it's a biologically inspired robot. What you see over here, this is what we want to do next. We want to fold up the legs and shoot it up for long-range motion. And it deploys legs. It looks almost like Star Wars. When it lands, it absorbs the shock and starts walking. What you see over here, this yellow thing, this is not a death ray. This is just to show you that if you have cameras or different type of sensors, because it is tall, it's 1.8 meters tall, you can see over obstacles and bushes and those kind of things. So we have 2 prototypes. The first version in the back, that's Strider 1. The one in the front, the smaller one, is Strider 2. The problem that we had with Strider 1 is it was just too heavy in the body. We had so many motors, you know, aligning the joints and those kind of things. So we decided to synthesize a mechanical mechanism so we can get rid of all the motors, and with a single motor, we can coordinate all the motions. So it's a mechanical solution to a problem instead of using mechatronics. So with this, now the top body is light enough, so it's walking in our lab. This was a very first successful step. It's still not perfected. It constantly falls down, so we still have a lot of work to do. The second robot I want to talk about is called Impasse. It stands for Intelligent Mobility Platform with Actuated Spoke System. So it's a wheel-leg hybrid robot. So think of a rimless wheel or a spoked wheel, but the spokes individually move in and out of the hub. So it's a wheel-leg hybrid. We're literally reinventing the wheel here. Let me show how it demonstrate how it works. So in this video, we're using an approach called a reactive approach. Just simply using the tactile sensors on the feet, it's trying to walk over a changing terrain, a soft terrain where it pushes down, it changes. And just by the tactile information, it successfully crosses over these type of terrain. But when it encounters a very extreme terrain, in this case, this obstacle is more than 3 times the height of the robot, then it switches to a deliberate mode where it uses a laser rangefinder and camera systems to identify the obstacle on the sides, and it carefully plans the motion of the spokes and coordinates it so that it can show this kind of very, very impressive mobility. You probably haven't seen anything like this out there. This is a very high mobility robot that we developed called Impasse. Isn't that cool? When you drive your car, when you steer your car, you use a method called Ackerman steering. The front wheels rotate like this. For most of the small, wheeled robots, they use a method called differential steering, where the left and right wheel turn in the opposite direction. For Impasse, we can do many, many different types of motions. For example, in this case, even though the left and right wheel is connected with a single axle, rotating the same angular velocity, we just simply change the length of the spoke, effective diameter, and then you can turn to the left or to the right. So these are just some examples of the neat things that we can do with Impasse. This robot is called Climber, Cable Suspended Limbed Intelligent Matching Behavior Robot. So I've been talking to a lot of NASA JPL scientists. JPL, they're famous for the Mars rovers. And the scientists, geologists, always tells me that The real interesting science, the science-rich sites, are always at the cliffs. But the current rovers cannot get there. So inspired by that, we want to build a robot that can climb unstructured cliff environment. So this is Climber. So what it does, it has 3 legs. It probably can't, it's difficult to see, but it has a winch and a cable on the top. It tries to figure out the best place to put its foot. And then once it figures that out, in real time, it calculates the force distribution, how much force it needs to exert to the surface so it doesn't tip and doesn't slip. Once it stabilizes that, it lifts the foot, and then with the winch, we can climb up these kind of cliffs. Also for search and rescue applications as well. 5 years ago, I actually worked at NASA JPL during the summer as a faculty fellow, and they already had a 6-legged robot called a lemur. So this is actually based on that. This robot is called Mars, Multi-Appendage Robotic System. So it's a hexapod robot. We developed our adaptive gate planner. We actually have a very interesting payload on there. The students like to have fun. And here you can see that it's walking over unstructured terrain. It's trying to walk on the coastal terrain, the sandy area. But depending on the moisture content or the size of the grain size of the sand, the foot's soil sinkage model changes. So it tries to adapt its gait to successfully cross over these kind of things. It also does some fun stuff. As you can imagine, we get so many visitors visiting our lab. So when the visitors come, Mars walks up to the computer, starts typing, "Hello, my name is Mars. Welcome to RoMeLa, the Robotics and Mechanisms Laboratory at Virginia Tech." This robot is a amoeba robot. Now, we don't have enough time to go into technical detail. Energy to the elastic skin to make it move, or use active tension cords to make it move forward and backward. It's called Chimera. We also been working with some scientists and engineers from UPenn to come up with a chemically actuated version of this amoeba robot. We do something to something, and just like magic, it moves. It vlogs, right? This robot is a very recent project. It's called Raphael, robotic air-powered hand with elastic ligaments. There are a lot of really neat, very good robotic hands out there in the market. The problem is they're just too expensive, tens of thousands of dollars. So for prosthesis applications, it's probably not too practical because it's not affordable. We want to go tackle this problem in a very different direction. Instead of using electrical motors, electromechanical actuators, we're using compressed air. We developed these novel actuators for the joints. So it's compliant. You can actually change the force simply just changing the air pressure, and it can actually crush an empty soda can. It can pick up very delicate objects like a raw egg, or in this case, a light bulb. The best part, it took only $200 to make the first prototype. This robot is actually a family of snake robots that we call Hydras, Hyper Degrees of Freedom Robotic Articulated Serpentine. This is a robot that can climb structures. This is a Hydras arm. It's a 12 degrees of freedom robotic arm. But the cool part is the user interface. The cable over there, that's an optical fiber. And this student, probably the first time using it, but she can articulate in many different ways. So for example, in Iraq, the war zone, there's roadside bombs. Currently send this remotely controlled vehicles with an arm. It takes really a lot of time and expensive to train the operator to operate this complex arm. In this case, it's very intuitive. This student, probably first time using it, doing very complex manipulation tasks, picking up objects and doing manipulation, just like that. Very intuitive. Now, this robot is currently our star robot. We actually have a fan club for the robot Darwin. Dynamic anthropomorphic robot with intelligence. As you know, we are very interested in humanoid, human walking, so we decided to build a small humanoid robot. This is in 2004. At that time, this is something really, really revolutionary. This was more of a feasibility study. What kind of motors should you use? Is it even possible? What kind of control should you do? So this does not have any sensors, so it's an open loop control. And for those who probably know, if you don't have any sensors and there's any disturbances, you know what happens. Yeah? So based on that success, in the following year, we did the proper mechanical design starting from kinematics, and thus Darwin 1 was born in 2005. It stands up, it walks, very impressive. However, still, as you can see, it has a cord, umbilical cord. So we're still using external power source and external computation. So in 2006, now it's really time to have fun. Let's give it intelligence. We give all the computing power it needs, 1.5 gigahertz Pentium M chip. And now Darwin 2 is completely autonomous. controlled. There's no tethers. It looks around, searches for the ball, looks around, searches for the goal, and it tries to artificial intelligence. Let's see how it does. This was our very first trial, and yeah! Yes. So there's actually a competition called RoboCup. I don't know how many of you heard about RoboCup. It's an international autonomous robot soccer competition, and the goal of RoboCup, the official goal is, by the year 2050, we want to have full-size autonomous humanoid robots play soccer against the human World Cup champions and win. It's a true official goal. It's a very ambitious goal, but we truly believe that we can do it. So this is last year in China. We were the very first team in the United States that qualified in the humanoid RoboCup soccer competition. This is this year. This was in Austria. You can see the action is 3 against 3, completely autonomous. There you go. Yes. The robots track, and they play a team play amongst themselves. It's very impressive. It's really a research event packaged in a more exciting competition event. What you see over here, this is the beautiful Louis Vuitton Cup trophy. So this is for the best humanoid, and we'll like to bring this for the very first time in the United States next year, so wish us luck. Thank you. Darwin also has a lot of other talents. Last year, it actually conducted the Roanoke Symphony Orchestra for the holiday concert. This is the next generation robot Darwin 4, much smarter, faster, stronger, and it's trying to show off its ability. I'm macho, I'm strong, right? I can also do some Jackie Chan motion, martial art movements. And it walks away. So this is Darwin 4. Again, you'll be able to see in the lobby. We truly believe this is going to be the very first running humanoid robot in the United States, so stay tuned. All right, so I showed you some of our exciting robotics work. So what's the secret of our success? Where do we come up with these ideas? How do we develop these kind of ideas? We have a fully autonomous vehicle that can drive in the urban environment. We won $500,000 in the DARPA Urban Challenge. We also have the world's very first vehicle that can be driven by the blind. We call it the Blind Driver Challenge. Very exciting, and many, many other robotics projects I want to talk about. These are just the awards that we won in 2007 fall from robotics competition and those kind of things. So really we have 5 secrets. First is, where do we get inspiration? Where do we get this spark of imagination? This is a true story, my personal story. At night when I go to bed, 3, 4 a.m. in the morning, I lie down, close my eyes, and I see these lines and circles and different shapes floating around, and they assemble, and they form different kind of mechanisms. And I'm like, oh, this is cool. So right next to my bed, I keep a notebook, a journal, with a special pen that has a light on it, LED light, because I don't want to turn on the light and wake up my wife. So when I see this, I scribble everything down, draw things, and I go to bed. Every day in the morning, the first thing I do before my first cup of coffee, before I brush my teeth, I open my notebook. Many times it's empty. Sometimes I have something there. If something there, sometimes it's junk, but most of the time, I cannot even read my handwriting. It's 4 a.m. in the morning. What do you expect, right? So I need to decipher what I wrote. But sometimes I see this ingenious idea in there, and I have this eureka moment. I directly run to my home office, sit in my computer, I type in the ideas and sketch things out, and I keep a database of ideas. So when we have these call for proposals, I try to find a match between my potential ideas and the problem. If there's a match, we write a research proposal, get the research funding in, and that's how we start our research programs. But just a spark of imagination is not good enough. How do we develop these kind of ideas? At our lab, RoMeLa, the Robotics and Mechanism Laboratory, we have this fantastic brainstorming sessions. So we gather around, we discuss about problems and solution problems and talk about it. But before we start, we set this golden rule. The rule is nobody criticizes anybody's ideas. Nobody criticizes any opinion. This is important because many times students, they feel uncomfortable how others might think about their opinions and thoughts. So once you do this, it is amazing how the students open up. They have this wacky, cool, crazy, brilliant ideas, and the whole room is just electrified with creative energy, and this is how we develop our ideas. Well, we're running out of time. One more thing I want to talk about is, just a spark of idea and development is not good enough. There was a great TED moment, I think it was Sir Ken Robinson, was it? He gave a talk about how education and school kills creativity. Well, actually, there's 2 sides to this story. So there's only so much one can do with just ingenious ideas and creativity and good engineering intuition. If you want to go beyond the tinkering, if you want to go beyond the hobbyist robotics and really tackle the grand challenges of robotics through rigorous research, we need more than that. This is where school comes in. Batman, fighting against the bad guys. He has this utility belt. He has this grappling hook. He has all different kind of gadgets. For us roboticists, engineers, and scientists, these tools, these are the courses and classes you take in class. Math, differential equations. I have linear algebra. Science, physics, even nowadays chemistry and biology, as you've seen. These are all the tools that we need. So the more tools you have, for Batman, more effective in fighting the bad guys. For us, more tools to attack these kind of big problems. So education, very important. Also, it's
Sir, video has stopped.
Sir, video has stopped. सर ने मुझे होस्ट बना दिया, सर चले गए। एंड
आ
कर
रहे
दो।
होंगे सर, रुक जाओ, आ रहे होंगे।
हाँ तो रुके होंगे। सेंडिंग अनदर लिंक, मैं एंड कर रहा हूँ।
भाई एंड ना करो यार।
बैठे रहो चुपचाप।